So today what we're going to do is we're going to take a look at precipitation reactions. We've done this before. We've done this where we take two different chemicals, we put them together, and we end up forming a precipitate. We have our solubility tables. Now there's a technique in chemistry where we take these two things, we put them together, and this allows us to figure out how much stuff we have. An example of this is in water. Sometimes we have salt dissolved in water, sodium chloride. And if you want to figure out how much salt is dissolved in your water, you can take a sample of that water and you can test it with silver chloride. Silver chloride will hopefully cause a precipitate to form. And when that happens, then you can take that precipitate, measure it, and then figure out how much salt was in the water. So it's an analytical technique that chemists use to determine how much stuff might be dissolved in the water. Now, what we're going to take a look at here is just a sample problem. Now, we've done problems like this in the past. We're just adding a new twist to this, and that is that we're mixing them together and we're actually measuring how much we mix together. So the example of this here is barium sulfate. We want to figure out how much barium sulfate is produced when we mix these two solutions together. Now, artistically, what we're going to have is a burette. Now, a burette, as you've used perhaps in your labs, is a glass piece of tubing. A glass tube looks like this. Okay, looks like this, and it has marks on it like this, so we can measure the amount of liquid here in the container. It has a little valve like this, and we turn the valve and the liquid drips down here into a container. Now in one of these containers here, it tells us that we have some barium chloride. So we have barium chloride, aqueous, dissolved, and we have 100 milliliters of it, and its concentration is 0.001 molar. And so we have that here in our burette. And in a second burette, we have another solution. So second burette here, we have another solution like this that will drip in, and like that. Go to school a long time to do this, I'm telling you. And in this one here, we've got iron sulfate. So iron Fe2SO4, 3, iron 3 sulfate. This is aqueous. And it's, let's see, we have 100 milliliters of it at 0.100 molar. Okay, so I'll go like this, and it's going to drip out. And then what we'll do is we'll mix these together into a container. And in that container, we're going to end up with our precipitate. And our precipitate is going to be, it tells us, barium sulfate. So we've got some barium sulfate, solid, precipitate forming. And the question is how much? How much barium sulfate do we produce when we mix these two together? So this seems kind of like a chemical reaction. It's going to be maybe even one of those limiting reaction type things. So the first thing I'm going to do is I'm going to write out the chemical reaction. Just going to kind of write out all the information that I know and then figure out how to solve this. So my chemical reaction is going to be barium chloride and iron 3 sulfate. Barium chloride plus my iron 3 sulfate and this is going to give me barium sulfate and what's left over is going to be iron ions and chloride ions. So it would be 2Fe 2Fe3 plus aqueous and 6 chloride aqueous and some balancing here I may have to put a 3 here and a 3 there. It's balancing this one out, I think. I think that comes out 6 chlorines and 6, and okay, that looks pretty good. Okay. Any questions so far? Okay. Now, what I know over here is I've got 100 milliliters and 0.001 molar. And for my iron 3 chloride over here, I've got the same thing, I believe. That's going to be 100 milliliters and 0.001 molar. And what I want to figure out over here is how much barium chloride I end up producing. Question. Is it 0.1 molar? Oh, yeah. Okay, yep. Thank you. Thank you. Okay, so 0.1 molar, 0.100, 0.100, and then over here, thank you, 0.100. Why didn't you catch that? Dude, we're like a team here. You got to help me out. Okay, all right. Next time, next one, right? You're gonna be all over it. Okay, you're gonna go like, dude, like, whoa, stop, right? Okay, help me out here. Don't let me look silly in front of like all these good people. Okay, all right. Okay, so here I have my solutions, and I can't just say, oh, well, I got 100 milliliters that, 100 milliliters that, must just be perfect, right? Because we know that we can't just compare grams to grams. We can't just do milliliters to milliliters. We need to do moles to moles. So we're going to have to convert to moles. Fortunately, we have a really nice equation that's going to help us with this. We have this equation that tells us that molarity is equal to moles over liters. And if we rearrange this equation, we can solve for moles. We can say that moles is equal to the molarity times the liters, right? So the concentration times the volume. So if I want to figure out moles of each of these, I just need to take my concentration times my volume in liters. So it's going to be 0.1 times 0.1. So my moles here is going to be, let's see, my concentration is going to be 0.100 molar times 0.1 liters, which gives me 0.01, I think, 0.01. Okay, so 0.01 moles. And then this is the same over here. It's going to be 0.01 moles. Okay. All right, so that tells me the number of moles of each of these I have. Can we figure out which one we run out of just looking at the stoichiometry? Is it the one on the left or the one on the right? Which one do we run out of? Barium chloride or iron 3 sulfate? The barium chloride. We run out of the barium chloride because it tells us with this here we need 3 times as much. So we run out of the barium chloride. So this here becomes our limiting reagent. So this is what we're going to run out of. This is what we run out of. This here is going to be our excess. So now if this is our limiting reagent, we can go through our stoichiometry and say if I've got 0.01 moles of barium chloride and it's a 3:3 ratio, that means I'll have 0.01 moles of barium sulfate. And I can just take my barium sulfate from moles and convert it into grams. So this would be a good thing if you've got a calculator to have that calculator out and follow along. Make sure that this guy does it correctly. Okay. All right, so I'm going to take my 0.01 0.01 moles of my barium chloride. And for every 3 moles of barium chloride, I have 3 moles of barium sulfate. And then every mole of barium sulfate is some number of grams of barium sulfate. And that's just barium plus sulfur and 4 oxygens. That's 233.39 grams of barium sulfate. And that should give us some number. And mathematically, these 3's cancel out. So it's really just 0.01 times that 233. Now, some people could probably maybe just look at that and just say, okay, I need to just move that decimal a couple of spots over. I'd have to put it into a calculator. I'm not that fancy. So what do we get for an answer? 2.33? 2.33 grams of barium sulfate. Nicely done. Okay, so that's just mixing these two solutions together. We're going to run out of the barium chloride. We'll have some excess iron 3 sulfate, and then we end up producing a certain number of grams of the barium sulfate. Okay. Now, some fancy terms. When we're mixing these things together, we call this a titration. The stuff in our tubes here that we're mixing or we're adding together, that is our titrant. That's the stuff that we are mixing together, and then our analyte is the stuff that we're trying to find out, what it is that we're trying to analyze. And so our analyte might be down here in the bottom of our tube here. So just some fancy terms. It's titration. Titrant is the stuff that's in the tube, and then an analyte is the substance that we're trying to analyze. You can do this with 2 different reagents and cause a precipitation reaction. That's one way of doing titrations. The other way, or the other technique that's often used, is mixing acids and bases and trying to figure out what is the concentration of an acid or a base. And when you do that, you'll often put an indicator into your analyte or your solution. So here what we have on the left-hand side here is an Erlenmeyer flask. You can see the bottom of the burette. And then there's a little bottle there, and that bottle is our coloring. And what that is, that's a pH indicator. It's usually phenolphthalein, and you add a little bit of phenolphthalein in there, and then theoretically, when you have your acid and your bases and they neutralize each other, it should give you a nice pink color. You should have a color change, theoretically. Now, I've seen this happen in labs where a student will start adding their acid and the base together, and they're waiting for this pink color to appear when the acids and the bases equal each other. And the pink color doesn't happen. And so they keep adding, they keep adding, they keep adding, and then eventually they run out of stuff in their burette. And then they're like, oh, okay, well, I'll just record that amount there and then throw some more acid or base into the burette and just keep titrating. And they don't get the pink color. And at some point, they ask their TA for help and say, something's not working here. I'm not getting the color change. What's wrong? Yeah, they didn't put in the phenolphthalein, right? They forgot to put in the pH indicator. And the TA will ask, did you put in the pH indicator? And the student will swear up and down, yeah, I totally did that. I did it. I swear to God, right? And the TA say, okay, all right. And then they just put a couple of drops in there and then bam, it changes color, right? And you're like, oh, it happens every semester. There's a lab group that does this. I don't want that to happen to you. So I'm telling you this story, okay? Make sure that you throw in a little bit of that pH indicator in there. How does this work? How does this work? Well, if you have an acid and you have a base and you mix them together, they should produce a salt and water. A salt is just a soluble ionic compound, and water. Now, the nifty thing about all of this is the number of moles are equal to each other. And we've seen this equation where we have M1V1 is equal to M2V2. And this is because the number of moles are equal to each other. And so theoretically, when we add an acid and a base together and you neutralize each other, you get to pH 7. The number of moles of acid is equal to the number of moles of base. And so that allows us to do a reaction like this. It allows us to use this equation, which makes our lives a little easier. We couldn't do it in the last problem because we didn't have an equivalence point. But we can do this with acids and bases. So now in this particular one, we have H2SO4. We have H2SO4, so sulfuric acid plus sodium hydroxide. And this is going to give us H2O plus Na plus and SO4. Let's see, 2 minus. Okay, we're forming water here. All right, I could say aqueous over here and aqueous over here, and I better not say aqueous here. Okay. And then I have some concentration of this that I don't know, but I have 15 milliliters. And my sodium hydroxide, I've got a concentration of that of 0.0973 molar, and I have 18.45 milliliters of that. Okay, and I'm trying to figure out what is the concentration here. What is the concentration of my sulfuric acid? Now, if I balance this equation out, I'm going to have to put a 2 here and a 2 there. So that means I have a 1-to-2 ratio here, stoichiometry. Because of that, I'm going to have to take my equation here, and I'm going to have to take into account the stoichiometry. The nice thing is it's really straightforward. Notice that the 2 is on the right-hand side here. Here's the 2. Okay, it's where my base is. So I'm going to go like this. There, now I'm done. Now if the 2 is over here, then I would put the 2 underneath this side. All right. So now setting this up, I'm just going to plug some numbers in here. I'm going to say that I have M1 times my volume 1, 15 milliliters. Okay, so I'll say 15 milliliters is going to be equal to my M2. So that's going to be 0.0973 molar times my volume 2, 18.45 milliliters, and then divide all of this by 2. Okay. And on this side here, if I wanted to, I might just say over here is my acid side and base side, just if that helps me to remember which solutions I'm using here. Okay, and then I just solve for M1. And when I solve for M1, I get 0.0598 molar H2SO4. That's the concentration of my acid that I started with. Sometimes students ask, why didn't you convert this into liters? And we could do that, but in this equation, the milliliters cancel out, so it doesn't matter. So you could leave it in milliliters. Okay, you get the same answer. All right. Any questions? No? Okay. Well, we have some practice on all of this, but before we get there, I want to show you something. I was on vacation with the kids, and the kids are like, "Dad, I'm really thirsty." I'm like, well, get something to drink. And we were at this amusement park out in California where they charge you like $5 for a bottled water. And as a parent, I'm like, suck it up, kid. When I was a kid, we didn't have water. Right? And they're like, give me $5 so I can get a water. So the kid comes back and shows me this. This is their $5 bottle of water. What's wrong with this? Besides the fact that it was $5? Yeah, what the heck is that? H2O plus? What? That chemically doesn't make sense. Oh, and then to make it even better, down on the bottom there it says pH balanced. Ooh, pH balanced water. Water is pH balanced. It's water. It's neutral. By definition, it's balanced. Right? They might have put a little label on there that said wet. Yeah, and I was like, are you going to drink that? This isn't, right? This is just like messing with my mind. No, that just can't work. That's just wrong. It's just wrong, 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 wrong.